Good morning, honors chemistry students. The next element that I would like to examine in our review of quantum mechanics and atomic structure is the sodium atom. So we're going to examine sodium, which has an atomic number 11, and this particular isotope that has a mass number of 23. Keep in mind that you identify once again an element based upon its mass number, so we'd refer to this as sodium-23, which has an atomic number of 11. Thus, the Z value is equal to the atomic number, which is equal to the which is equal to the number of protons that are positively charged, which is also equal to the number of electrons which are negatively charged, and in this case, those numbers are 11. 23 is what we affectionately refer to as the A value, which is the mass number, which equals the number of positively charged protons plus the number of neutrons, which in this case and in all cases are neutrally charged with no charge. We've identified that the number of protons in this particular isotope is 11, and the number of neutrons can be determined by the difference between the mass number and the atomic number, which in this case is 12. So this particular isotope has 11 protons and 12 neutrons for a total of 23. So the mass number for that particular isotope is 23. As we continue to move across and down the periodic table, sodium is the first element we're going to examine that's a member of row 3, which is also called period 3. Sodium has enough electrons to start filling the third energy level. That's why it's placed on row 3. We say it's a member of column 1, also known as group 1A. Once again, the A elements are referred to as the representative elements. And you can think of it this way, in that the Roman numeral attached to the letter represents the number of valence electrons for that particular atom, which in this case is 1. So you can surmise that sodium has 1 valence electron. We say it's a member of the alkali metal family of elements, which are all elements that react vigorously with water. And include lithium, sodium, potassium, rubidium, cesium, and francium. As with all the elements on the Meet the Elements lab, I want you to diagram an 8 ELD. I want you to represent the nucleus for sodium with a box divided in 2. The top box represents the number of protons, the bottom box represents the number of neutrons. We've identified that this isotope has 11 protons and that it has 12 neutrons, and both those values should add up to a mass number of 23. So the nucleus consists of 11 protons and 12 neutrons. We have to place 11 electrons and energy levels by the Aufbau principle. So we fill the energy level that is lowest in energy first, closest to the nucleus, which in fact is the n equals 1 energy level that holds a maximum of 2 electrons. Once its energy level is complete, by the Aufbau principle, you start filling the next lowest energy level, which would be the second energy level. These 2 electrons represent the 1s. We will put 2 electrons in the 2s. Then we will put 1 in this 2p, 2px, 2py, 2pz. Go back and pair those up by Hund's rule, which states that Every orbital in a sublevel must have one electron before you pair them up. And so now we have accounted for 10 electrons with 2 on the first and 8 on the second or L shell. So therefore we can safely say the first energy level is filled, the second energy level is filled, and then we go to the next lowest energy level by the Aufbau principle, which would be the third energy level, which has just 1 electron. And we say that that energy level is the n equals 3 energy level, or the M shell, KLMNOPQ. I'm not going to go ahead and draw that entire circle because I'm circle challenged, and it's best that I don't do that. But suffice it to say, we say that sodium's a member of group 1, A, because it has 1 valence electron. This valence electron is the electron on the highest occupied energy level. Thus, I also want you to represent the electron dot representation of sodium, which includes its symbol plus a dot to represent the 1 valence electron. Once you've done that, I'd like you to go and represent the placement of electrons in sodium on a diagram called the orbital notation diagram, which basically diagrams the placement of electrons and energy levels according to the Aufbau principle and Hund's rule. And according to the Aufbau principle, we are to build up the placement of electrons and energy levels that are lowest in energy first, before we move to higher sublevels and higher energy levels. By now, quantum mechanically speaking, we know that quantum mechanics predicts that the first energy level has just an S sublevel, which holds 2 electrons of opposite spins, one going up and one going down, to account for the repulsion of electrons that have similar charges in an orbital. Nextly, once the first energy level is filled with 2, you move to the second energy level, which has 2 sublevels, an S and a P that has 3 orbitals predicted by quantum mechanics, one that lies along the X, one that lies along the Y, and one that lies along the Z. We can already see that the 2s sublevel has 2 electrons, and then we need to place the P's, one in this X, one in that Y, one in that Z. By Hund's rule, each orbital in a sublevel gets 1 electron before you pair them up. You place another electron going down, down, down. We have a total of 10 electrons, 2 in the first energy level, 8 in the second. So both of those are filled. So the only place we can place the next electron is in the third energy level, which also has a 3s sublevel that can possess 1 valence electron. So this electron is this electron, which is that electron. To write the address for that electron, we use what's called the electron configuration. Which accounts for the placement of electrons in the given energy levels, sublevels, and orbitals. There are 2 electrons in an S sublevel on the first energy level, so we would begin by saying the configuration starts with 1s2, which, by the way, is also the configuration of helium. Once we've filled the 1s, you move to the second energy level and fill the 2s, which has 2 electrons in an S sublevel on the second energy level. Then you move to the next highest sublevel, which is the 2p, which holds 6 electrons, so we would say 2p6. And finally, given that the first energy level and the second energy level are filled with their full complement of electrons, the next electron is placed in the 3s S sublevel. So we would read the configuration of sodium as 1s2, 2s2, 2p6, 3s1. You never know, you might be asked to produce the configuration of sodium on an AP chemistry exam. That being said, we can also write this in shorthand notation because 1s2, 2s2, 2p6 is the same configuration as that of neon. So we simply could say this is neon 3s1, and the outer configuration is 3s1. It has one valence electron and an s sublevel on the third energy level. That being said, the next representation I want you to move to is the Cartesian coordinate system, which starts to get a little bit more complicated here just because it's visually challenging. The Cartesian coordinate system is the XY coordinate plane. We can display the first two electrons orbiting the nucleus, which is seen as the vertex of this, by placing two dots. Remember, you can visualize this two-dimensional circle as a three-dimensional sphere as well. We know that two electrons can exist on an S sublevel, on the second energy level, and then you have to start placing electrons in the 2p y sublevels, one along the X, one along the Y, and if I'm good today, not too bad, one along the Z axis. So now we can begin to fill the P's. One in the X, one in the Y, one in the Z, and then go back, go back and pair them up. Now we filled the first and second energy level, and then the placement of the next electron goes in the third energy level and an S sublevel, like so. A little bit circle challenge, but not too bad. Gets placed right there. So this valence electron is this valence electron, which is that valence electron, and that one, and that one. And that is the electron configuration of sodium, which clearly illustrates why sodium is in column 1 and group 1A, because it's got one valence electron in its highest occupied S or P sublevel. The next element we're going to take a look at would be magnesium, which is the neighbor to sodium.